Shipping today is not confronting a single dominant challenge. It is facing multiple crises converging simultaneously. Climate change is driving intense decarbonization pressure, while at the same time exposing ships to more frequent and more extreme weather events. Meanwhile, much of the global fleet is operating well beyond its original design life, with aging structures and machinery under increasing stress. Human factors have become equally critical. Crew shortages, fatigue, and rising system complexity mean that safety now depends as much on human-system interaction as on physical hardware. Under extreme operating conditions, small errors or degradations can escalate rapidly into cascading failures. At the same time, modern ships are no longer purely mechanical assets. They are cyber-physical systems, dependent on data, connectivity, and software, and therefore exposed to cyber, data integrity, and system interaction risks. The key point is this: these challenges do not act independently. They interact, reinforce, and amplify one another. What we are facing is not a collection of isolated problems, but a systemic crisis, and systemic problems demand system-level solutions. For more than a century, we have treated ships as static products. We design them, build them, certify them, and then operate them until problems appear. This model was effective in a more predictable world, but it is no longer adequate. The ships of the next century will operate for 50 years or more in an environment defined by uncertainty. Climate extremes, rapid technological disruption, progressive aging, and changing human roles. Under these conditions, the key challenge is no longer simply how to design a ship or how to operate a ship. The real question is how to care for a ship throughout its entire life. Structure, machinery, human operators, and the environment cannot be treated as independent domains. They are tightly coupled, evolving together as a single living system. Performance, safety, and sustainability emerge from their interactions, not from any one component in isolation. This marks a fundamental shift from ships as objects to ships as systems, and from engineering as construction to engineering as lifelong care. Everything that follows in this lecture is an attempt to answer this systems question. When we talk about decarbonization in shipping, the discussion is often reduced to a single question: which fuel should we choose? LNG, ammonia, hydrogen, methanol, or even nuclear are frequently presented as competing answers. But fuel switching alone will not deliver true decarbonization. True decarbonization requires fundamental changes in ship design philosophy. Enlarging ship size and extending design life from today's 25 years to 50 years or more are essential for CapEx optimization, allowing the initial investment, particularly for low carbon and nuclear technologies, to be amortized over much longer operational lifetimes. At the same time, longer design life enables OpEx optimization through reduced repair frequency, minimized downtime, and more efficient maintenance strategies. Every alternative fuel introduces system-level trade-offs: higher capital cost, lower energy density, new safety hazards, and increased operational complexity. If we focus only on emissions at the point of use, we often displace carbon and risk elsewhere, into construction emissions, fuel production, port infrastructure, or shortened asset life. These challenges become even more critical for SMR-powered ships, where decarbonization must be balanced against radioactive leak prevention, robust containment, and continuous safety assurance. Likewise, fully autonomous Level 4 ships, operating without crew on board, cannot rely on traditional human-centered inspection and intervention. For both cases, real-time, life cycle, intelligent healthcare, and operational management is no longer optional. It is indispensable. This is why decarbonization must be treated as a life cycle systems problem, not a component-level choice. CapEx, OpEx, safety margins, operational reliability, and total life cycle emissions must be optimized together, continuously and adaptively. The ships of the next century will only be genuinely low carbon if they are designed as integrated energy and information systems, supported by AI and digital twin-driven real-time monitoring and decision-making across their entire lifespan. In this sense, decarbonization is not merely a fuel problem. It is a systems engineering and operational philosophy problem. Safety in shipping has always been tested by extreme events: collisions, groundings, flooding, and loss of stability. What has changed is the frequency, intensity, and unpredictability of these events. Climate change is exposing ships to harsher seas, stronger storms, and more complex operational pressures than those assumed at the design stage. Crucially, modern maritime accidents are rarely caused by a single failure. A collision may trigger flooding, followed by power loss, degraded human performance, impaired decision-making, and ultimately cascading system collapse. Yet traditional safety frameworks still tend to address structures, machinery, and human factors in isolation, struggling to capture these coupled failure mechanisms. The stakes rise even higher with energy-dense propulsion systems and nuclear-powered ships. In these cases, safety margins are narrower and the consequences of failure far more severe. Preventing failure alone is no longer sufficient. What is required is a fundamental shift in safety philosophy, from designing ships to avoid failure to designing ships to survive failure. This means inherent crashworthiness, real-time situational awareness, and system-level resilience that allows ships to absorb damage, adapt to evolving conditions, and recover safely under extreme and unpredictable scenarios. Most ships are originally designed for a nominal service life of around 25 years, yet in practice, many continue operating for 40, 50 years, or even longer. This widening gap between design intent and operational reality has become one of the most serious and systemic challenges facing the maritime sector. As ships age, they inevitably suffer from corrosion, fatigue cracking, machinery degradation, and growing uncertainty in structural capacity. Yet despite this increasing complexity, our primary safety mechanism remains largely unchanged: periodic inspection and survey. These inspections are intermittent, often subjective, and provide only a snapshot of a continuously evolving system. Crucially, damage does not wait for surveys. Corrosion progresses, fatigue accumulates, and machinery degrades continuously, while many critical failures initiate and develop between inspection intervals when early warning signs remain undetected. As global fleets continue to age, the fundamental question is no longer whether ships can operate longer. The real question is whether we can know their true condition in real time. Without continuous health awareness, life extension becomes a gamble rather than a rigorous engineering decision. As ships become more complex and more digital, the human role on board is not diminishing. It is intensifying. Crew numbers are decreasing, yet cognitive demands are rising sharply. Seafarers are expected to monitor multiple interconnected systems, interpret large volumes of data, and make high-stakes decisions, often under conditions of fatigue, isolation, and time pressure. Many maritime accidents today are not caused by hardware failure alone, but by breakdowns in human-system interaction, misunderstood alarms, delayed or inappropriate responses, and cognitive overload at critical moments. These failures emerge not from incompetence, but from systems that were never designed around human limitations. This exposes a fundamental misconception in conventional engineering. Humans are still treated as external operators of ships, rather than as integral components of the system itself. In reality, safety is an emergent property arising from the interaction between humans, machines, software, and the operating environment. If we want safer ships in the next century, we must design systems that support human performance rather than overwhelm it. Human-centered engineering is therefore not optional.